So problem number 2 from exam 2 shows a horizontal track that's frictionless, a spring launcher for a mass M that then goes around the vertical loop, and asks you first, what is the work done by the normal force as this object goes around the loop? Now, that should be an easy one. You've actually seen this before. Work is defined to be F. The force dotted with displacement. The dot product tells you that only components of force along the direction of displacement can give you work. In this case, the normal force is always perpendicular to the surface of the track, so that you have no work done as by the normal force as the particle moves along the track. So the work of the normal force is 0. And the justification is this concept or equation. B says, what's the work done by the force of gravity on the block? Well, you should know that the work done by gravity, well, the same reason that we have up above, depends only on the force of gravity, which is mg, times the displacement in the direction of gravity, which is just the change in height. And so in this case, the height is increasing. It's going to 2r from 0, or at least the change is 2r, and the force of gravity is down, so the force of gravity points opposite to the direction of the displacement. So you have a work done by gravity of negative 2 mgr, and the 2 comes because the height is twice the radius, or the diameter of the circle is twice the radius. Okay. Now C, oh, by the way, the problem warns you to be careful about the sign, so you need to get that sign right. C asks, what's the block speed, Vp, at the top of the loop? Well, you could try to solve this with Newton's laws, I guess, but you'd be in trouble pretty quickly. It's an obvious case where you want to use conservation of energy. There are no non-conservative forces acting on it. There's no friction. You've got gravity, which we can take into account with its potential energy. We've got the spring, which we can take into account with its potential energy. And we've got kinetic energy, and that's basically what we're after, kinetic energy, because when you're asked for the speed Vp, that's equivalent to asking for 1/2 mvp squared, or the kinetic energy. So we're going to use the concept that the final energy equals the initial energy, where you define where final and initial are for your system, plus any work done by non-conservative or external forces, but that's 0. Okay, so we can write down, let's also write down that we'll assume the potential energy of gravity is going to be equal to 0 at the base, or at the bottom of the ramp, where the spring launcher is, the bottom of the loop, where the spring launcher is. And that's just a convention. You could pick it other places, but that's going to make life a little bit easier for us. That choice will make life a little bit easier. So with this choice, we have E naught, which is what the energy when the spring is maximally compressed, but the block's at rest, will be equal to the potential energy of the spring. The mass is at rest, so it's got no kinetic energy. The potential energy of gravity is 0 because we chose it to be 0 there. So the total original energy is 1/2 kL squared. Now the final energy, in this case final, will be at point P, will be equal to the kinetic energy there, which is 1/2 m, the velocity at point P squared, plus the potential energy of gravity there, which is plus 2 mgr. And remember, potential energy equals negative work done by the force, so you can see again why the sign changes from part B to part C when you go from work done by gravity to the potential energy of gravity. And we also have we don't have any spring energy because the spring is no longer part of the system whenever the mass is at the top. Okay, so all we have to do now is use our conservation of energy concept, E final equals E naught, which tells us that 1/2 mvp squared plus 2 mgr equals 1/2 kL squared. Remember, what you're asked for is VP, and we can solve this equation for VP in terms of other things that you're presumably given, or at least you're asked to express VP in terms of them. So this is just a little bit of math. Multiply everything by 2 over m and take the 2 mgr to the other side. So let me just do that in one fell swoop. And I'll have to have a square root there because we'll be solving for VP squared. So VP will be the square root of, again, multiplying KL squared by 2 over m will get me KL squared over m from this term. And then minus 2 mgr. I've got to subtract mgr from both sides and multiply by 2 over m. So the 2's will cancel. I'm sorry, the 2's will multiply. You'll have 2 over m, so you'll have minus, the m's will cancel, minus 4gr. And that's the answer. That's VP expressed in terms of K, L, M, G, and R. So that's the answer to part C. Part D asks you for the normal force whenever the mass is at the top, and it encourages you, or tells you actually to start with the free body diagram. So let's just draw the top of the loop. We have a mass m in there. It's going around a circle with a velocity VP. What forces act on it? Well, there's gravity, mg down, but there's also a normal force from the track because it's in contact with the track, and so that contact force from the track on the mass has to be pushing down, okay? And those are it. But what we know, or should know, is that the sums of the forces, now I should also, I guess, pick a direction for things. Let me pick, since I've been doing it in lecture, let's just pick an r hat direction up and an x hat direction to the right. So r is radially out from the center of the loop. Now you could call it y, you could do other things, it's not critical really. So the sums of the forces in my r direction, well, I've got a negative n, a negative mg, because those both point in the negative r direction. Those have to sum to m vp squared over r. And we know that because those two forces have to sum to supply the centripetal force, which supplies the centripetal acceleration, which is v squared over r. Okay. So, given this, all you're asked to do is to solve for the normal force, and you have an equation which can be simplified to show that. So the normal force, we can multiply through by negative 1 if you like and keep n to the left. The normal force will be equal to, I'm sorry, I forgot something here. This is also a negative sign on that side because the acceleration is in my negative r hat direction. So multiply through by negative 1, that changes everything to plus here. And then we have the normal force equals m vp squared over r. Okay, and then you have to subtract mg from both sides. Now, you're not supposed to answer in terms of VP. You'll get most of the credit, I think. You should get most of the credit if you do. But what we really should do is take our VP, or VP squared, from up above and plug that in and give an answer in terms of things you were given in the problem statement. So if I do that, I have m over r. VP squared is KL squared over m minus 4gr. That's the answer to part C squared. Minus mg, and I can simplify this. I can now write this as, well, the m's cancel in the first term, so I have KL squared over r. The second term, the r's cancel, so I have minus 4mg, and then I have minus mg. So the final answer really should be written as KL squared over r minus 5mg would be the answer to part D. By the way, I almost gave you a part E for this, which said, what would you have to do with L to have the mass barely make it around the top of the circle? That would have required you to, how far would you have to compress the spring to do that? All that would have required was to set n equals 0, then write KL squared over r equals 5 mg, and you could then solve for L. In that case, L would have been the square root of 5 mg r over k. But I was trying to make the exam a little shorter and stopped with this part D. That's it.